Welcome everyone. So today we will be solving one of the problems. Uh, it tackles two concepts. It's the concepts of infinite series and uniformly continuous functions. So the first thing that you have to understand here is that there is a boundedness condition whenever we are actually working on uniformly continuous function over a semi-closed, semi-open interval. So let me put it down like this. So suppose the interval that we have was not from 0 comma infinity. So one thing that you can actually understand here is this, that the continuity or uniform continuity totally depends on the domain of the function. Okay, so like you can take the same f and you can define it from a to r, and you can take that same f, I mean the same function, I'm not even disturbing the function, and you can actually define it to a to some b that is subset of r. That does not change the property of the function f. That is one of the things that you should first observe. So why am I actually saying it? Like if the function is 0 comma infinity to r, if it is uniformly continuous, so without changing the function, if I know that the function's range is in between 0 comma infinity, which is a subset of r, if this is the subset of r which contains the range of f, then this will also be uniformly continuous. Okay, so and this goes vice versa. Like if I have 0 comma infinity to 0 comma infinity uniformly continuous function, then I can take 0 comma infinity to r as a uniformly continuous function, provided that I do not change the range of my function. So now if so, then one of the main observations, if f is 0 comma infinity to r a uniformly continuous function, this implies that f from r is a uniformly continuous function, because uniform continuity, it depends on the interval. So if it is uniformly continuous on the bigger interval, it will obviously be uniformly continuous in the smaller interval. Now from here we actually pick up our problem. So the thing is that if from 1 comma infinity to r is uniformly continuous, this implies that there exists an m greater than, such that mod of f of x is less than mx. Okay, so this is one of the properties of the uniformly continuous function. How we are actually going to use this in our problem is something like this. So suppose I have f of n plus 1 minus f of n to be less than some n. Okay, so because it's a uniformly continuous function, I will have this for all n belongs to n. So this is a property. So this is one of the properties of uniformly continuous function. Because it is uniformly continuous, I have this. So now what you can actually do is something like this. Since it's defined from 1 to infinity, we can actually check for what happens at f of n minus f of 1. So f of n minus f of 1, you can actually write it like this: f of n minus f of n minus 1 plus f of n minus 1 minus f of 1, right? So from the triangle inequality, you will get this equals to f of n minus f of n minus 1 plus f of n minus 1 minus f of 1. Now, as you can see that since this is a proposition that we are actually using for all n belongs to n, this is less than m plus m, right? So see what happens. You take n minus 1, it is m, so it's practically 2m, correct? So if you continue breaking it, then you are actually breaking this into 2, this into 2, but fixing if n and if 1. So we actually need this. So in the end, what does it happen? In the end, you get something like this: 1, which is less than in m, right? So like, I mean, this thing you will break it as f of n minus f of n minus 2 plus f of n minus 2 minus f of n minus 1, and then this one as well. So it will go like this. So you will have n distinct pairs like this. So the moment you have this, this will actually imply that for all your n, the f of n, this thing lies between f of 1 plus nm, and this is the thing that you want, that the bound on f of n. So no matter whatever the uniformly continuous function, no matter what uniformly continuous function you take from 1 comma infinity to r, modulus of f of n, so that function is always bounded. That's the thing. So this function is always bounded no matter whatever as your n. Okay, so the now the so from here, what do I have? From here I have that if n is bounded for each n. Okay, so now what do I need? I need this series to be convergent. But for this to be convergent, what do I need? I need limit n tends to infinity mod of f of n to be tending to infinity. But this will not be the case because I have actually proven that fn is bounded for each n. So the moment I have fn to be bounded for each n, this element, as we have mentioned, f of x is less than mx. So the thing is that 1 by f of n is divergent because f of n, the mod of f of n will not go to infinity. So but the thing is that whatever we have done up until now, it's from 1 comma infinity to r, but the question asks from 0 comma infinity to r, or in generally 0 comma infinity. So the observation here is that if there is no uniformly continuous function here that satisfies the question's property or the hypothesis, then there should not be something here as well, because if it existed here, then it would have existed here as well. So if not this, then not this. So with this argument, we actually prove that this is false. So thank you for joining. We will meet with another problem in the upcoming session.